All right, we're going to go ahead and get started. So I wanted to set a little context for what we're going to be presenting today. The way it worked out with the scheduling and stuff, there's effectively 3 presentations in one here, so we've got to kind of stick to 15 minutes, 15 minutes, 15 minutes to get through the material. Up front, I'm going to cover a little bit of a teaser overview of Red Hat's perspective on big data as one of the hottest topics in the industry and what we think about it, et cetera. In the middle, Tushar is going to talk specifically about a little primer on what Hadoop is, and then talk about the problem of multi-tenancy management for Hadoop and how it relates to some of our grid technologies. And then at the end, Matt's going to clean up and show an actual live working demo on EC2, and we're going to pray to the demo gods everything works well. And we're going to show a Hadoop cluster being managed on an EC2 instance using our MRG Condor solution. So I'm Scott McClellan. I'm in the CTO office for Red Hat, joined in February. I own the big data strategy for Red Hat world, company-wide. We're not announcing a bunch of products or a specific strategy here today. Today what we are going to do, though, is walk a little bit through our perspective on big data. It's a real hot topic in the industry, and use that to, and I'll hopefully, as you guys have been wandering around attending other tracks, you'll notice there's a lot of tracks here or sessions here at the conference that are related to big data. We didn't have time to pull together a specific big data track, but in a sense there must be 15 different presentations here at Red Hat Summit that are directly related, whether it's some of the stuff from Developer Day about polyglot computing using OpenShift and MongoDB together, to other tracks on NoSQL solutions, and there's some stuff on Red Hat services and how we've put together solutions for big data, et cetera. So there's quite a bit of stuff. This is the only place where I'm giving a little bit of an overview on our point of view. So just quickly before we start, by show of hands, how many people in the room think they're comfortable with what big data is? Oh, that's good. How many people are comfortable that they know what Hadoop is and a fair amount about Hadoop? That's approximately the same number, which doesn't surprise me, because today Hadoop is so hot in the marketplace, and it's probably the lead dog example of a big data technology crossing the chasm for commercial adoption, that in many cases big data conference and Hadoop conference is exactly the same attendees, so that's not surprising. How many people in the room would consider themselves significant experts in Hadoop or big data? I'm hoping for a lot of hands for this one. Oh, darn. Because the reason why I was hoping for a lot of hands there is we're going to be hiring, so, so I didn't get a lot of leads out of that, but that's good, So one last question is, how many people think big data is all hype? Maybe all hype like cloud was, or similar amount of hype to cloud was, versus something that, let's start with hype. How many people think it's hype, and then I'll say how many people think it's real? Hype. A few hands. And by the way, there's no right answer to this question, because in anything that's this hot in the industry, there's definitely a certain amount of hype. How many people think it's real? That's good, and that's encouraging. Okay. So like I said, our agenda kind of flows. I'm going to hit a few topics on big data at Red Hat. Like I said, this is not a big announcement of a all-encompassing strategy, just kind of maybe laying some track for where we're going in people's mind. So with that many people saying they're familiar with big data, this slide's not going to shock anybody, but unless you were under a rock or something, there's a real data explosion going on out there. And I'm not going to try to cover this in any depth, and I think everybody would just accept it and agree with it anyway. But a couple of things that are true is that the rate of growth of data is just explosive. It's exponential. This is true in almost every industry. For the sake of time, we took out some other slides we had that showed if you broke down the whole world by different sectors, this problem would be the same in almost every sector. It's not like it's just something that the web guys have and nobody else has this problem of exploding data. I think it's obvious what's driving it, but just to make sure we're all on the same wavelength, we kind of went a few years ago, or several years ago, most of the data was coming from more or less B2B interactions. Then you had a lot of B2C interactions. Then you had a lot of customer-generated content. And now part of what's driving this stuff extremely nonlinear is a lot of machine-generated data. where it's coming from machine-to-machine interactions, it's coming from sensors, it's coming from consumer devices. Recent examples include things like set-top boxes, which are instrumented for analytics, so that when your ads are being shown through the set-top boxes, if you change channel or turn the volume down on the TV, that's feedback into the analytics engine driving the, so there's another surprising source of big data. It's having social networking is being used for manufacturing process control. I mean, all kinds of crazy stuff. So it's in every industry, right? And a couple of things, I didn't put the sources in here, but if you just want to read good reads, there's a McKinsey study on big data. It's very comprehensive, breaks it down by industry and CAGRs. There's also IDC, EMC study that's been refreshed every couple of years called The Digital Universe. Extraordinarily good read if you're wanting to read some of the information on the growth of data. Just generalizing though, there's these two terms, structured and unstructured data, which are terrible terms, because the truth is almost all data actually has structure. When people say structured data, really what they mean is data that's been stuffed into a traditional relational database. And when they say unstructured data, they mean everything else. And the term kind of implies that the other data doesn't have structure, but that's not true, it does, Log files have structure, they have fields for timestamps and user information and stuff like that. It's counted as unstructured data, but it has structure. Video files are unstructured data, but they have structure, MPEGs, all kinds of stuff. Sensor data is structured, everything is pretty much structured. So structured data is a term that's a proxy for relational database data. And honestly, while that's been growing for decades, the growth is relatively flat, as represented by the thing on the line on the bottom. And the line on the top is how unstructured data is growing explosively steeper. There's really good factoids running around that the amount of data in the digital universe has doubled in the last 2 years. There's stuff like that, right? Those kind of explosive growth rates are not true for relational database, for data that's been kept in relational databases. So one way to look at this is traditional approach to getting business insight from your data was to stick the data into a data warehouse and then use BI, EDW type tools and ETL processes, et cetera, very mature industry to get insight from your data. The problem is look how much data is not in a relational database. So if the definition of naive is making decisions based on less than all of the available information, then if you're not looking at the information other than the information you've put into your EDW, then you're getting effectively more naive over time. This is the premise, right? And so in a way, that's the business challenge and the business problem and why there's so much interest in big data, right? And I'll add another couple of perspectives off of that in a minute. Probably anybody that said they're familiar with big data has seen the 3 V's or the 4 V's, volume, velocity, and variety. And the 4th V, if it's included, is value. So some people say, well, we've been looking at data for business insight for decades. So what's the big deal about big data? And I think what makes it different, and another way people talk about it sometimes is big data is stuff that is going to require an approach different than the traditional approach. So if you could get the insight you needed from your data using traditional tools and technologies, that's not big data, that's BI. If it's going to require a different approach, and then the things that could drive you to requiring a different approach are things like volume, the sheer volume of data. That's the first V. We're talking massive quantities. Terabytes is not a big number anymore. You're up in the many petabytes of data on an individual customer base, not customer, but a given deployer of a big data solution will have petabytes of data, not petabytes per customer. That would be a real problem, right? No. The second problem is speed. Either the ingest velocity of the data or the egress velocity of the data is extremely high. Either you've got to get data pumped into your source, or into your thing to do analytics on it extremely fast, or there's something about your application that requires you to draw an insight from that data very quickly. Either one is a velocity problem, and that's typically not addressable with standard tools. And the third one is variety. The data is coming from lots of different sources. It's in lots of different formats. Sometimes it's got lots of gaps and holes, and missing pieces and invalid data in it. So all of those things contribute to variety, which make traditional tool approach very difficult. And then value, which is not on here, But one of the other things driving the difference in approach is the cost effectiveness of using open source software on scale out commodity solutions. So the hardware is cheap, the software is cheaper for addressing the problem versus a very expensive proprietary hardware or software for the traditional approach. So there's value driving it. That's the other difference. And I would say, okay, great, you're amassing all this data. Where does that kind of leave you guys, if you're today? And I think the reality is getting from probably where you are today to an amazing utopian end goal of having every piece of data someplace and you're analyzing every piece of data for drawing business insight. That's a multi-step journey. You're not going to get there all at once. I think key is to take control of the situation, is to get a proactive strategy in place to start working on the problem, to stop the getting increasingly naive. So kind of keep pace. You have a question? Did everybody hear the question / observation? So I'll paraphrase it back. So it's kind of the postulation is that with traditional BI tools, you're pretty confident in the quality of the insight you're drawing from your data versus the suspicion with some of these new tools that you might not be as confident in the insight. And I guess that's hard to argue on one level because the technology is new, the domain is new. And versus you're comparing it to something quite mature, However, I would argue that in many ways the quality of the insight should probably be better because of the diversity of the data sources being analyzed. I mean, it's you can, I don't know, it's probably some Bayesian theory or something would back me up, but I'm not an expert in this area. That that if you're drawing a conclusion from more data, it's more likely to be higher quality. But you're right. I mean, it's an emerging field. The skill set required to use these tools is quite high compared to the traditional tools. And in some cases, we're counting on this new class of analysts called a data scientist and some new tools. So I think for a little while, there'll be some working itself out. You know what I'm trying to say?
Systematic bias,
yeah.
Not just poor quality.
Yeah.
Systematic biases because you only look at 3/4 of the sources.
Yeah. Right.
So anyway, I don't have a magic answer to your question. I think that it'll work itself out as these technologies are increasingly crossing the chasm and put into use, right? And people will, as they prove themselves to be reliable insights, they'll become more and more trusted, and where they're wrong, the natural feedback mechanism will yield better techniques, okay? So anyway, my point is that, yeah, there's a lot of new technologies, and I'll show you a chart on that in a second. Not everybody's going to suddenly, have a giant Hadoop cluster and put every piece of data they've got into it. You're going to ease into this. You're going to try to get a plan in place to get the situation under control is what I'm advising. I think one of the things to keep in mind is the key to this whole thing, this whole big data thing, is the flexibility that's enabled by these tools. A lot of these tools, the magic is that you're able to get some insight from the data without having to decide a priori up front what the structure should be for the data. The problem with having to decide on the structure up front is you have to know all the questions you're going to ask of the data before you stuff it into the database. Otherwise, when you come up with a question you wanted to ask and the schema is not well suited to asking the question, you're back to square one, starting over, defining a new schema, going through your ETL process again. So a part of what the big breakthrough is here is this stuff allows you to be flexible. And if you think that way, that's a goal for your company, and that's something enabled by these technologies, I think that's important. Okay, just quickly, because we're not doing a real deep thing on big data, I think there's 3 classes of new technologies that are really new, right? There's Hadoop, and then there's what the 451 group calls the new data space, and it goes by lots of names. It's got NoSQL and new SQL and columnar stores and
key value stores, et cetera. So that entire complex NoSQL, new SQL space, I've simplified into two categories. NoSQL databases, which allow you to store and query your data without a relational schema, but do not support SQL interfaces, and OLAP optimized database type solutions that maybe they put it in a columnar store rather than the traditional way of storing the data, but they do support SQL. So on the left you have new data stores that structure the data differently. They don't require a schema to be defined, and they're very, very fast. In the middle you have things that are fast, not as fast as the NoSQL databases, but are, and not quite as scalable, but have the advantage of supporting SQL. So therefore, they work very well with your legacy reporting tools, et cetera. And on the right, you have Hadoop, which is not nearly as fast as either of the other two. It's more actually oriented toward batch, can support an enormous capacity, and is not really it's not really a database. It's more of a database and compute architecture combined. So with Hadoop, it's a place you can store the data and run jobs in place on the data. The first two solutions are really data-only solutions. So you got data-only, and compute and data. On the left, you have things that are extremely fast but don't support SQL. In the middle, you have things that are not quite as much faster than Hadoop, not quite as fast as NoSQL, support SQL semantics. And on the right, you have Hadoop. So all three of these categories of technology are important in big data. And they have kind of, this is a gross oversimplification, but each has its place, is my point. So if you need really fast access, real-time-ish access, because you've got to paint a web context for a user or a mobile context for a user instantaneously, not wait while you query something. It's the technologies on the left or the middle. If it's something that you can look at a mass of data, figure something out, and then get back to somebody on, it's more Hadoop. So Hadoop is more batch-oriented. Does that make sense? Okay, and from Red Hat's point of view, that diagram, which was really oversimplified before, that represents in the market 80-plus technologies. Honestly, there's many open source and a few proprietary solutions across that continuum. But what you see, and my point on this first bullet, is the whole data tier is really changing from Red Hat's perspective. Traditionally, the dominant piece of software and dominant animal on the data tier was the relational database. Now there's a lot of different solutions that are kind of less general purpose, more special purpose, extremely scalable, extremely cost effective, and dominated by open source. And so, first of all, there's a whole new set of challenges, which we kind of went through, and our big data strategy needs to pull together solutions to address those challenges. Secondly, this point I was just making about the world is no longer dominated just by relational database technologies, so it's an opportunity for Red Hat to bring to the forefront many of these open source technologies and stand behind them in the way we traditionally have for open source. Third point is that data analytics and business intelligence really needs to be flexible and scalable, the points I made earlier. The advantages of these new approaches are much more flexible and much more scalable and much more cost effective. Finally, the fact that we see this as a very open source dominated landscape puts Red Hat in a good position. And the last point is our customers and partners are asking us to solve this problem. I mean, as we interact with various partners, they're saying, why aren't you doing this? Why don't you do that? So I think the market is really expecting us to come to market with a strong big data position. So this directionally is where we're coming from and where we're going. Today, what we have is Linux, Rev, Res, Red Hat storage, and a portfolio of Red Hat cloud products and Red Hat middleware. They're all connected to the big data movement in the ways described in this slide. Big data is predominantly dominated by Linux deployments. And as it's really crossing the chasm into mainstream enterprise, we're seeing the dominant Linux underneath big data deployments being RHEL. That hasn't necessarily been true rearward looking as more early adopters, but as it's moving into the production phase, it's really true. The Rev, the key benefit there is the extreme high performance or low I/O overhead of the para-virtualized KVM solution. It's a very good fit for big data because it gets you, these tend to be very I/O intensive workloads, and running them on in a virtualized environment on Rev is a good fit. Red Hat storage is going forward. One of our tenets of our strategy is to really kind of reduce the distance between data silos, to be able to have a Red Hat storage be a general purpose data store, but be able to integrate MapReduce and other data, other workloads that exploit data locality directly onto the Red Hat storage clusters. So we were going to tech preview, and I think we did tech preview here at the show, the capability of running MapReduce jobs directly on a Red Hat storage cluster as an example. So, I mean, our strategic direction is to reduce the distance between the silos and really leverage Red Hat storage in our big data strategy. And finally, InfiniSpan and Hibernate are good examples of existing middleware technologies that are quite relevant in this space, but really to even further exploit deeper integration of all of these technologies with big data solutions. So this just kind of sets the stage for where we're going. And I'm pretty sure we're out of time for my section, so I'll transition it over to Tushar. So thank you. We have questions at the end, by the way, if you have any.
Thank you, Scott. Thank you, Scott. Again, quickly, Tushar Kutarki. I'm the product manager for Red Hat Grid here at Red Hat. What I'm going to talk to you really, as Scott mentioned, what we are trying to do is we are at Red Hat, we are trying to bring in all these technologies that we already have, and solve big data challenges. And one of the ones that he mentioned really was trying to get big compute, which Grid is all about big compute to big data. So that's kind of my underlying theme for this whole thing. Quick 1-minute Apache Hadoop tutorial. The Apache Hadoop really, many of you probably know, is an open source framework for intensive distributed, compute-intensive distributed applications. It has two components, MapReduce and Hadoop Distributed File System, which is HDFS. And MapReduce is a paradigm for parallelizing your workload so that you can get data fast, data access fast, or you can make insights into data very fast. And HDFS is really the underlying file system, which is Java-based, incidentally, and it's in userland, which is used by this entire framework. As you can see on this figure, on the right side you have the you have data coming in. You just color-coded it, maybe yellow, green, red, blue. It gets into HDFS via this name node, which is which has all the metadata about where data is going to be stored, and the data itself, as you can see, goes on these data nodes, and obviously the red, blue, and I have simplified it to show that the data is distributed across commodity hardware there. On the left side, now, if you have jobs, you want to get insights from this data, and their jobs, let's assume, has some kind of affinity. Some, again, simplified model, green and yellow, maybe blue and green. That's the data that they need. They MapReduce job tracker. MapReduce is a programming framework for analyzing this. It has the map step and the reduce step. And once they land to the job tracker job tracker spawns off multiple requests for maps and reduce. Those are called task trackers. And the map task get done, and then they feed it to the reduce task, and then the insight is got via MapReduce. So that's kind of a quick 1-minute Apache Hadoop tutorial. What I'm really here to talk about, though, is what are some of the challenges that we think people who are deploying this or who are planning to deploy it, Hadoop, in their environments may start to see or already seeing. So this is just a story of how this whole thing of the deployment of Hadoop in a typical organization, and some of you who have Hadoop running might recognize this. So you have different departments. You have accounting here. You have finance there. You have, let's say, marketing, sales, different departments. They set up. They have data. They have data to mine. They set up Hadoop clusters, as you can see here, and basically soon what happens is what is known as, and then the Hadoop cluster keeps growing, and what you have really is what is known as the multi-instance and the multi-tenant problem, which I'm going to talk about next. The multi-instance problem really has to do with the fact that when you have multiple Hadoop clusters, your users, let's say in the accounting department, are limited to the compute and data in that particular Hadoop cluster, whereas somebody in the sales department is limited to that. What happens with that is, if you kind of know multiple queues, what happens in a bank, you have like multiple tellers. You could be in one queue, whereas the other queue is empty, right? I mean, or it just has two people, and you don't want to shift that quickly. So anyway, so it basically causes access to capacity limitations, right? And so causes needless waiting. Even though there is capacity, you are not able to use it. The other thing that might happen is there could be islands of data, and so the data is distributed across different, and so that limits your analytics, right? I mean, the accounting department, let's say, has data and it wants to use data from the finance department, and they are not able to do it because of these islands. And then also basically what happens is that you're limiting the cluster to MapReduce only. I mean, whereas MapReduce is a great framework, many of you would know that MapReduce is not like panacea. There could be even now, or there could be in the future, more analytical frameworks to analyze the data. So I think basically what we are saying with this multi-instance is, with this you are limiting yourself, you're reducing the returns from your infrastructure by siloing it up like this. The other thing is the flip part of it is also the multiple, so once you have, Hadoop becomes successful, more and more people use it. I know some of you I talked to in the room who have said that it has grown from like one or two users to hundreds of users now. So once that happens, you need to have things like, you get into this multi-tenant problem. There are a number of users using it, number of departments using it, number of groups using it, and you want to really have that access control. You would need to have departmental quotas. You might have user quotas. You want to have some kind of a fair share, again, as you might expect of any grid environment like that. And then once you do that, you would want to also have metering information, maybe which could be used for reporting and then for chargebacks. You need to have that, and then you need to be able to work in a heterogeneous environments. And by this we mean that today you deployed something, a Hadoop cluster. Let's say you used, I don't know, the latest Intel chip, and every 2 years tick-tock, Intel comes with the next chip. It keeps growing, so you get this heterogeneous environment pretty quickly, and you need to be able to deal with that. So what we are proposing really is that what you really need to do is you need to consolidate. You need to consolidate all your clusters into one supercluster, or maybe you federate it. Either ways, you need to consolidate, and you need to share the data, not only with MapReduce, but other analytical frameworks, other jobs, and you want to institute controls and policies, because again, as the number of clusters are increasing, a number of users are increasing, number of departments are increasing, it becomes a very important thing. The next, so how do you do it? So what we are proposing really, the way to do it is for consolidation and sharing, you need a common interface layer, which basically can act as a layer for job submissions, if you will, for monitoring and for reporting of jobs. Then you need intelligence built into the engine, if you will, which can basically match those jobs to appropriate resource in appropriate places, and while also doing things like the controls and policies that you have instituted while respecting that. Then you need once it's been figured out, what you next need is, once you know where this job has to land, you need to be able to send that job over to that machine, if you will, and keep track of it. So you need that ability to dispatch. And then finally, you need to be able to manage these multiple jobs, users, groups, and so on and so forth, and obviously resources. So while some of you might already be doing it in some way or fashion, what we find is that Red Hat, and we'll talk about Red Hat Grid real quickly, but Red Hat Grid has a lot of these capabilities already, and one of the solutions that we are proposing today with the existing technology is running Hadoop on Red Hat Grid. This is not to say that obviously Hadoop is also going to keep evolving, and obviously you will see some of that go back into Hadoop also, but right now this is what we are proposing. So Red Hat Grid, a brief introduction. Red Hat Grid is based on a Condor project, which is very rich, 25+ year history. It's got a vibrant a community around it, and it's considered a leader in big compute, if you will, in distributed computing and in grid computing. So real quick, Red Hat Grid, so what we talked a little bit about this, but basically what we have is a job submission interface wherein you submit the jobs. You have an interface, and then you have policies. We're going to talk about that on the next slide. You can have workflows, and workflows really means that when you submit jobs that are related to each other, say job A depends on job B, you don't want to run job A until job B is completed. So that's workflow management. Once the job is submitted, you want to know about what's happening to the job. That's the event management piece, and then you want to store that information away so that you can access it for analytics, for billing and metering that we talked about, and for capacity planning. And obviously once you do all this, you need things such as configuration management to distribute all the configuration, and you need, and so obviously we have that, and we provide tools for troubleshooting. So that's Red Hat Grid in a nutshell. So the architecture, as you can see, it's very modular and distributed. The whole notion is you submit jobs to the scheduler up there, which is, and then the scheduler is going to ask somebody called a negotiator about what's the right resource, match this job to appropriate resource, and independently all the nodes which we are going to run this job are reporting into the collector over here on the left about their status, how many CPUs they might have, how many resources they might have, and all that is collected in the collector, and the negotiator now queries the collector and gets that information and tries to match that job, the best possible resource for that job, given all the other conditions, right? I mean, it might have restrictions on how much memory it needs. It might have restrictions placed by the administrator. Given all that, it tries to find the best available resources, and it gives out a claim back to the scheduler saying that, hey, this is the resource, this is the claim for the resource, go ahead and run your job. That's when the scheduler goes ahead and schedules the job directly to the execute node. The bottom line, really, what I want to say really is that, as you can see, it's very distributed, and that's why it scales very well. And that's why it has very good high availability features, which we are not going to delve into, but just in the interest of time, just know that it has it. So one of the core pieces that I really wanted to talk about here is what is known as fair share scheduling. And that really is that when a job lands, there are three things that the grid is looking at, Red Hat Grid, or the Condor really is looking at. And that is really, it's looking at the job's priority. And these are specified by the job itself. What's the priority of the job? What are the kinds of resources that it needs? It expresses a desired a desired, and a minimum set of resources that it needs, and then it can say things like timeouts and runtime limits. And then the machine itself, where the machines can be advertising things like when they want start and stop times, for instance. That is, if it's a shared machine, for instance, you do not want maybe you do not want to run it at a certain point of the day. You do not want to be taking jobs. So those are the things that it does. And then the administrator institutes policies and quotas. And so what we are doing really here is that with fair share scheduling, scheduler basically assigns the job to an available resource that meets all these requirements and gives it, and also tries to find the highest rank, which is the most desirable resource for this particular job, and gives it that based on policies and quotas set up. So that's basically, Matt, how much more time do we, 2 more minutes? Okay, good. So some of the Red Hat Grid features that I want to talk about really is, these are some of the features. Dynamic slots is the first one up there. Dynamic slots allows you to basically take a system, a resource, and split them into slots, right? So for instance, if you have an 8-core machine, you could have 8 slots, for instance, and each slot will then get a core and, let's say, 1 gig of memory out of the 8 gig that is completely available. So that allows you to basically then each slot becomes a resource to which you can send a job. And so dynamic slot, and that's the static way of doing it. Dynamic, basically what allows you to do then is to have it as fungible, so that if a job comes in and it needs, let's say, 2 cores and 2 gigs of memory, it gives out 2 cores and 2 gigs of memory is used up, and the 6 cores and 6 gigs of memory are left in the available pool, and the next job comes in which only wants 1 core and 1 gig, it gets that, so it keeps chunking it. So that's dynamic slots, and it basically increases the utilization. Ultimately, it increases the utilization because a job, when it lands on a machine, it's not very likely to be using all 8 cores. So this allows you to use keep the utilization of the machine also very high, at a machine level. Some of the other things we talk about, the one interesting thing is this federated clusters, which allows you to take these multiple clusters and federate them. So the job that lands on this cluster might say that, hey, I want to use a resource in another cluster because maybe the data is available there, or maybe because there is some additional capacity available. So we can take care of that with Red Hat Grid. That's one thing I want to talk about. You can do things like compute on demand, which basically allows you to reserve a pool or a set of resources ahead of time, so that you can get to it. You can use it later. And then there is the accounting part, which I talked about briefly, which allows you to not only obviously track usage, but also use it for billing and metering purposes. So what are some of the deployment models for Hadoop? You start with the isolated clusters here on the left. We talked about that, and then you might choose to do as the next step, you might still want to have those multiple clusters, but you want to just federate them, right? And that allows you to use that spare capacity, allows you to use the data. Or you might, as a next step, you might want to have it all under one large grid, which is the full consolidation on the right. Obviously, each individual company and each individual use case will be different, but this is something that is available. Having said that, I want to pass it on to Matt. He's going to talk about Apache Hadoop on Red Hat Grid, a brief architectural overview, and then he's going to do a demo. Thank you.
Hi, is this on? Okay, so I think I've got just about enough time. This is the part where everybody's going to get to laugh as I try to attempt a live demo across the internet to EC2, setting up things. So this is basically a very brief overview of what I'm going to do. The idea is I'm going to set up a pool, or actually I've already set up a pool, of a grid pool inside EC2 of about 20 nodes. And in that, I'm going to start up an actual Hadoop cluster. So this is a HDFS instance and a MapReduce instance. The interesting part of this is that, the interesting observation is that each of the components that you can see here, the job trackers that are part of the MapReduce, and the name nodes and the data nodes that are part of the HDFS instance, are themselves can be encapsulated as jobs. And once they're encapsulated as jobs, you get all of the policy functionality, all of the lifecycle functionality, all of the scalability capabilities, all the migrating capabilities that Grid provides you. You get this for the actual services that are required to create a MapReduce HDFS instance. So basically, this is exactly what I said I was going to do. I'm going to go through, I'm going to set up the HDFS, the MapReduce, and then run some workload on that. So bear with me for just a second, because this keyboard is really small, and I'm used to I'm used to a trackpad. But so the first thing I'm going to do is I'm actually going to go out into. Is this visible? Should I try to make this a little bit bigger? Visible? Okay. So here's the first fun step of seeing how slow the wireless connection is in this room. So what have I done? I've actually connected to the kind of a head node for Grid deployments in EC2 right now. So you can see, if you're familiar with Condor at all, I know some of you are, some of you are not. I can actually explore the system itself. So Condor Q is going to list out all of the jobs that are submitted and in some state of running or completing in the system. Condor Status is going to list all of the resources that I have available to me. In this, in case you can't see it, I've got 38 available. Each one of them has 2 resources, and I'm not running anything on this kind of head node that I'm running the demo on. So another little diagram of what a Hadoop MapReduce cluster looks like is you actually have the HDFS layer where you keep all your data, which is made up of a name node and some number of data nodes. These are just essentially services. The MapReduce layer of this is made up of a job tracker and then some number of task tracker services. And it's important to point out that there's a data dependence where job trackers actually require a name node to be running. So what we've done for this demo is created some porcelain around Condor, so we can provide basically kind of like an HD and a Hadoop view on all of the data that's being stored on the Grid layer. And so, for example, if I actually, there we go. Oh, sorry, I forgot one thing. I need to actually log in as a user to do this. So the first piece of porcelain I'll show you here is the name node, and it's pretty simple stuff at the moment. This is basically you can view, you can start, you can stop name node services. So the first thing I'll do here is actually start a name node. And what's happening is it's being submitted to the Grid software itself. So it starts to show up in the queue, the list of jobs. In this case, it's started running pretty quickly. You can also kind of look at it from a Hadoop, a little Hadoop interface. So this is actually already started running, and it reports back because it's basically being scheduled out onto this infrastructure. I'm not exactly sure where it was scheduled. The software took care of that. But it reported back in the web interface location. So I can actually click on this, and it'll pop up with your familiar name node interface if you're familiar with using Hadoop. So once I've got that, the second piece that I said I needed to start up was a data node. And so there's porcelain for that. To start up a data node, I need to tell it where the name node was that I started. And I started that, I gave it an ID of 45. So I'll start up data node, and actually I'll start up multiple data nodes because just one is no fun. So these are basically, we're looking up the location of the name node, and we're submitting a bunch of data nodes that are going to attach to that. You can see them both in this interface. You can see them in the underlying grid interface. They're running already. And you can see them having joined the name node itself. So I've got about 2 terabytes of storage on those 5 nodes that are now in an HDFS cluster. So to actually get this running, the next step to show you the ability to actually run the MapReduce, I need to start the job tracker, which I mentioned is the kind of the main piece for the MapReduce layer, and then I'll start up the task trackers. So as you'd expect, there's interface for this. It looks very similar.
Question in the back.
Question in the back.
Or there.
So yeah, actually the control script that starts up the name node when it's scheduled out does the formatting. So, sorry. Safe node is off. Yeah. Actually, in the pure setup, when it's starting up fresh in this situation, there's no data loaded into it. It doesn't necessarily transition through the safe node state. Okay, so I'm going to start the job tracker. And to do that, like I mentioned before, I actually need to tell it where the name node was, so that was still 45. This is gonna boot up. You can all pretty much figure out what's happening at this point. It's being packaged up as a job. It's being submitted to the system, and it's running already on the infrastructure. Kind of like on the grid infrastructure, you can actually see where these things are running, or that's from the queue view. You can also look at from the inventory view. You can see that some of these resources are claimed and they're doing some work.
You want to also show the GUI?
Yeah. So just like the name node, the job tracker, when it starts up, reports back its actual location. So we can just pop right over to the web UI for the job tracker. Here, obviously not too interesting yet because there aren't any task trackers. I'll start one of those up next. And to start up a task tracker, I have to tell it which job tracker it's going to connect to. And I'll just start 5 of these as well. And once again, kind of like repeating the same process. They're all getting packaged up. So all of the functionality that you have for tracking and managing jobs in the grid infrastructure is available here. So I can actually show you that because this central manager node that I created is a full grid deployment. So we can actually look at the grid web user interface. No, don't do that. You can see that we've actually started up 12 jobs. We've got some number of resources. Some of them are used. Some of them aren't used yet. But now at this point, the job trackers probably started up. We can see that there's 5 of them attached to the job, the job tracker itself. And from here, I actually have a fully operational HDFS instance and MapReduce instance. So what I'm going to do is I'm going to do a little configuration where I'm going to set up basically the local environment so that I can use the standard Hadoop commands to interact with both the name node and the job tracker. To do that, it's called it setup conf, and we remembered that the name node was 45 and the job tracker was 51. So all this is doing is this is querying the underlying grid infrastructure, finding out the actual endpoints, and then sticking them in some your standard MapReduce site configuration and core configuration files. So I've jumped over here to another terminal just so I can I can do the submission, the actual MapReduce run from this side. So that's user. And I've got, this is essentially just a untarred instance of the Hadoop tarball that I grabbed from Apache website. So from here, I can do things like DFS admin and see the name node, or look at what's in the queue on the job tracker. But more interestingly, what I can do is I can just start up a simple MapReduce job itself. So I'm not going to do anything too fancy here. Try to keep this a little bit simple, so more likely to work. But I'll just run MapReduce bench with about 500 map tasks and some small amount of input data lines. And essentially, if you're familiar with Hadoop at all, right now what's happening is the MapReduce job is starting up. It's being submitted to the job tracker. If I refresh here and scroll down a little bit, you can actually see it starting up here in the job tracker. You can move into it. You can see it's actually already running. There are 10 running. Some starting to complete. And that's basically a simple, very, very small cluster. But if I go back here and I look at the grid interface, I actually see that I have a number of resources available to me right now. And these are things that other people could be using, but they're not using right now because I'm the only person using this system. So I'm going to take advantage of the fact that there's available resources.
One more question.
Yep. Sorry? So you can do affinity based on, I can go into the details more. We actually have a lab right after this where we talk about the underlying grid infrastructure and how you can include locality information, rack style information in it, and then use that as part of the scheduling decisions. So, the data actually, in some of these cases, they are. In some of them, they aren't. You're never going to be able to get a perfect one-to-one mapping of your data to where the task trackers are. So the task trackers that have your data might be used by other task trackers that are running on the same data. So there's a kind of a spectrum of how close you can get to perfect mapping. And we can talk about that, like the scheduling capabilities behind that if you want. Before this actually finishes, I wanted to demonstrate how we can take the task trackers and actually increase was it 51?
Yeah.
Okay. Now it's, so what I'm doing is I'm realizing that there's extra available resources, and I'm saying, okay, I'm going to scale up my job, my MapReduce cluster by just adding 10 more nodes to it. So I've just added 10 more nodes. They're going to show up actually pretty quickly here. We'll start seeing this should go from 10 running to 26 running, and it'll probably go all the way up to 40 or 38, 40 or so running. And this is going to just overall take advantage of available resources to get my job done more quickly. And conversely, I could cut down on the resources that are used by the job tracker. So I think I should probably stop there so we have some more time for questions. Basically, yeah, you can see actually since those started up, the completion rate increased, so the throughput's going up. So, yeah. Questions? So yeah, so basically the general approach is starting with the command line, making sure everything works, because we find that a lot of people who interact with the software, well, they need high-level UIs for showing people and often for reporting. On a day-to-day, the existence is in a shell on a command line. So basically, you're right. Right here. I'm showing the underlying grid infrastructures interface, and then I'm peeking through and I'm looking at the Hadoop interface. We'll have to be looking at how we can actually represent the Hadoop workload that's running more as a first-class citizen within the grid UI as well.
Was your question partly about having an integrated UI that's a Hadoop UI that's grid aware, basically, in the future?
Where it's like we have a couple of different UIs, maybe
Yeah.
a command line going on. But,
Yeah.
I mean, once it becomes like really customer friendly, you have one UI that you can also maybe even select jobs through. That's what we're trying to get.
I mean, certainly that's the direction that we want to head. I mean, but we certainly also want to get your feedback. I mean, as we said, this is all new, exciting, but at the same time, we'd love to get Red Hat customers' feedback so that it looks like that's what you were saying in this particular case is helpful, and certainly we'll be looking into that.
But I think what we were really just trying to show in the demo is how kind of compatible in a way, using grid to manage a large pool of resources, you can quickly use that to treat Hadoop as a service that you want to deploy onto that shared pool, use all the functionality we already have, and benefit from that in managing your Hadoop cluster or clusters. I mean, tighter integration down the line is all stuff we would do. This was just it makes sense, it's just a demo, right? Yeah.
Any other questions?
Well, thank you.